Hello, everyone. Can you hear me? Yes, excellent. A warm welcome to April's meeting. I am being Colin for today. Colin is in the Netherlands. So have we got anyone who is new or who is a member but has never attended a meeting before? Can you raise your hand? Quite a few of you. Okay, well, welcome. My name's Rachel Dutton. I am the committee member that looks after outreach. Can all the committee members just wave your hands or stand up? There's a few of us around. We've got Pam, we've got Martin. So do feel free to come and say hello and to mingle. The format of the evening is that we have a talk and then we have tea and coffee and then we do a WhatsApp and events, space news, and I'm going to be talking about outreach and the various things that we've done over the last month, and I've got lots of eclipse images. So our speaker for tonight is from the Surrey Space Centre, which is just over that way somewhere, if I've got my directions right. So he's going to be talking to us about solar system exploration. Just a little bit more about him. So this is Dr. Nicola Baresi. He attained his PhD from the University of Colorado Boulder following an MSc degree in physics from the University of Padova in Italy. He later worked on real-life satellite missions to the moon and Phobos as a postdoctoral fellow of the Institute of Space and Astronautical Science of JAXA in Japan. Since September 2019, he's been working at the University of Surrey, where he is now a senior lecturer in orbital mechanics at the Surrey Space Centre. So a warm welcome.
I'm going to try to do it like this, okay? Can you guys hear me in the back as well? Fantastic. Louder? Okay, I'm Italian, so it will be easy for me to speak a bit louder. Move my hands around, see how it goes. Is it okay if I share my screen? Okay, let me try to do that. Back in small mode. It's okay. You can probably go to view. Yeah. And then, is that better? Yes, we just remove that one. Okay, fantastic. So let me start by saying that it's a really great pleasure to be here tonight. I've always been keen on finding out more about the Guildford Astronomical Society, and what's the best way to do it by giving a talk about my passion, which is exploring the solar system. So thanks, Rachel, for the introduction. As she said, I'm a senior lecturer in the Surrey Space Center just across the street here. And what I do is to try to enable the exploration of the solar system. So let me start by asking you a question. Who of you have heard about the term astrodynamics? Okay, a few terms. I think the Martian helps a bit because there was a key figure that will pop up in my presentation later on. But in a nutshell, astrodynamics is a core subject within the space engineering field, which is very vast and multidisciplinary. They try to deal with the study of the motion of objects in space. All right. So what we are trying to do on a daily basis at the Surrey Space Center, at least with my group, is to estimate what kind of torques and forces are acting on our satellites so that we can predict how satellites behave in space. And our mission is to better understand, estimate, and control the dynamical evolution of objects to enable space exploration. Why would you care about astrodynamics? Well, the thing is that the solar system is actually fairly big, right? I tried to put the closest thing to scale that I could find on the web, and you can't even see what the orbit of the Earth looks like. It's so tiny in there, right? If the solar system were to be as big as this room, the distance between the sun and the Earth is probably about like 15 centimeters. That tells you how much things is out there for us to explore, and also how much there is still to understand. We only had a limited number of satellites that have explored beyond Earth orbit. So I hope that you're looking forward as much as I am to coming missions that are going to be solving some of the key mysteries of our solar system in the upcoming years. So in today's talk, I'm going to try to give you essentially a primer of solar system exploration. I decided to divide my talk in about 5 parts. First will be launch vehicles. Then I will go into some basic orbital mechanics techniques, including some spacecraft propulsion technologies. and then talk you about interplanetary mission design and deep space navigation, because I can then wrap it up and show you how we can use these key ingredients to support some of the upcoming missions that I've been working on as part of my daily activities at the Surrey Space Center. So part one, launch vehicles. As you can imagine, any rockets, any missions start from the launch pad, right? We need to find a way to escape the gravitational attraction of the Earth in order to insert our satellites into orbit. And the core idea is essentially things that we call in physics as conservation of linear momentum. Think about a cannonball that is being fired by a cannon. So as you can imagine, as you fire the cannonball into one direction, because of the conservation of the linear momentum, the cannon is experiencing a reaction in the opposite direction. It kind of like recoils, right? So as much as you push the cannonball away from your cannon, the cannon is accelerated in the opposite direction. That's basically rocket propulsion for you. The idea is that we want to expel our propellant as far away and as fast as possible to get a recoil into the opposite direction. And hopefully, we're going to generate enough thrust to defeat gravity, which is the thing that takes the rockets attached to the Earth. In fact, in rocket science, the cannon is the rocket, and the rocket is usually harboring your satellites at the top of its cone. We call this like a fairing, and sheltered into the fairing of our rocket are our precious satellites and their precious instruments that allows us to explore the solar system. So what we want is to expel mass and therefore propellant with as much power as possible to get a recoil in the opposite direction. The way we do it is an idea that came to Robert Goddard, which many consider to be the father of space exploration. He essentially had the idea to generate a combustion, right? He has like a fuel, typically liquid hydrogen, mixing with oxygen. They create a very fast chemical reaction with an explosion. And as long as we can control this explosion, we can generate a lot of heat and a lot of like exhaust, which are expelled away from the combustion. And if you use clever designs such as this nozzle here, we can accelerate the exhaust of our combustion in the direction that we want and as fast as possible. All these key ingredients are what allowing Goddard at the beginning of the 20th century to generate the first sounding rockets, essentially. Now, unfortunately, there is an interesting story behind this, because when Goddard came up with these first designs, the US government didn't really invest too much into it. He was essentially relocated into the Mojave Desert, where he could carry out his experiments without really endangering the population nearby. Legend goes that in one of his experiments, he actually set a roof on fire, and he was actually declared a dangerous personality. As often happens, history comes back and kicks you. Because what happens is that the idea of Goddard were actually very influential and were taken over by key people in Europe, like Hermann Oberth and Werner von Braun, which were some of the two brightest minds behind the German V2 rocket. Now, it's an interesting story because the German V2 rocket was obviously used for the worst possible intentions, right? But historically, it's the first intercontinental ballistic missiles that was ever built. And it actually turns out to be the first man-made artificial object that actually crossed into space. Nowadays, we define the boundary of space as what we call the von Karman line. Is about 100 kilometers in altitude from where we stand today. Like if you go up 100 kilometers, that's as close as space it is. It's not farther than, I guess, Guildford to Newcastle, right? That put things into perspective. But in order to go up by 100 kilometers, you need to generate this power with these combustions that I was just talking about. So the V2 rocket is the first man-made object that ever made it into space. It was used for the very wrong, goals, but it opened the door to space exploration. Surprise, surprise, when World War II was won by the Americans and the Russians, there was literally a race to secure as much V2 hardware and personnel as possible. Because by the end of World War II, it was clear that this technology would be crucial in creating geopolitical influence over the coming decades. So what is now known as Operation Paperclip, 1,500 scientists, including Werner von Braun himself, were relocated quietly to the United States of America. And despite being officially a Nazi during World War II, Werner von Braun actually ended up making a career in the United States and even became the head of the rocket propulsion group. In fact, he's the father of what is still, close by, one of the largest rockets that has ever built, the Saturn V, which you see here in this picture in comparison to the V2 rocket that is at the top of these slides. Now, the principle of Saturn V and all of the rockets that you see on these slides is actually the same as the Feed 2 rockets and the original idea of Goddard. You have big combustion chambers. We have like a liquid hydrogen or fuel that comes in contact with an oxidizer, create a controlled explosion, and then the exhausts are pushed out to defeat gravity and escape into space. Since Saturn V, space exploration has evolved. We have the space shuttle program, which you also see into the slides, and more players coming to the party. Until very recently, I will say about 10 years ago, even private companies joined the frenzy. Everybody has probably heard about Elon Musk and SpaceX. Why are they so crucial for space exploration? Well, they essentially changed the game. They came with an idea that originally was thought to be unphysical, which is like to return the rockets back to Earth and reuse them for launch. The reusability of the rockets has caused what you see here in the top right corner, this key trend, which to me is the first enabling technology for solar system exploration that we're going to overview tonight. What you see on the y-axis of this plot is the dollar per kilogram, how much it costs in dollars to put a satellite into orbit. And the scale is logarithmic, so it actually scales order of magnitudes up. So unsurprisingly, Saturn V and the Apollo program, right, were very expensive. That's one of the reasons why also the space shuttle was shut down. Because if you look on this plot, the cost per kilo of the space shuttle was by far the highest that we experienced in space exploration. Now comes Elon Musk and his fleet of reusable vehicles like Falcon 1, Falcon 9, with this crazy idea of returning some of the rocket parts back to Earth to reuse them for future launches. And you see this drastic decrease in the cost per kilogram. Who in this room has heard about Starship? Okay, as many hands as astrodynamics, which is good. So Starship is the next biggest rockets that has ever been built, right? If you put it into scale, it's even bigger than the Saturn V rockets that propel humanity to the surface of the moon. And why Starship? We are very excited about it, and we think it's revolutionary, is that he has the potential to drop the dollar per kilogram cost in the $100 regime. How is that of an enabler for space exploration? Unsurprisingly, we now see mega constellations being launched. Starlink is these new thousands of satellites, tens of thousands of satellites, in fact, that are constantly floating around the Earth, which I assume you as astronomers don't like particularly. Yet they're changing services on Earth. They're providing connectivities in remote rural areas. They're changing our understanding of the Earth as a system. And more of these mega constellations are unfortunately bound to come. Thankfully, and thanks also to your efforts, we're trying to do the best that we can to mitigate the light pollutions that they generate. So I'm confident that we will be able to find a solution that will make everybody happy. Point is that now space is becoming much more accessible. And in fact, it's on the mouth of everybody around the world. If you're not investing into space nowadays, you're literally falling behind, which is great if you happen to be a space engineer like me. Okay, so we can now move on to the second part of my talk, in which I want to talk about orbital mechanics and space propulsion. The idea here is that in the first part of this talk, I hopefully convinced you that no matter what is the launch vehicle that you select, one way or another, you will be released into orbit around the Earth. But what does entering into orbit means? Well, it essentially means that as soon as you're released from your launch vehicles, you carry enough speed to essentially counterbalance gravity. You're falling back on Earth, but you have so much speed that you're actually falling back into an orbit around our planet. The speed that you need to carry is an insane amount. It's 26,000 kilometers an hour. That would be good for being on time in my meetings, I will tell you, but it's challenging to get you up there. And the first that ever reached these orbital altitudes was Sputnik 1, which you see here into this animation. The first satellite that was ever launched on the 4th of October, 1957. And since then, we have made use of the real powerhouse of space, which is gravity. Everything can stay in orbit and move around in orbit because of the gravitational attraction between objects with masses. We owe the original idea to Newton, a fellow British, that in the 1600s came up with the theory that two bodies with mass exert a force upon each other. Me and Rachel are exerting a force upon each other at this very moment. We both have a mass, m1 and m2, and we are relatively close to each other. So the distance between the two bodies actually plays a role into this force. But there is another term, which we call the gravitational constant. And this gravitational constant is extremely small, like 10 to the power minus 20. Like if you have to write this number, you need to draw a 0, a comma, and then 19 0 before your first significant digit. That's the reason why we don't feel attracted to each other on planet Earth. The force is so small that the friction between my shoes and the ground is not enough to pull me towards you. Now take this concept further and think about planets in the solar system. Well, planets, moons, and even like stars carry enough mass to generate enough gravitational force. And in fact, we do feel it. We are attached to the ground. Gravity is pulling us down because of the mass of the Earth that counterbalance this tiny gravitational constant. Now, what I'm showing here is the manifestation of what some of you may know as the Newton's third law. Newton's third law says that if a body exerts force on another body, then the other body exerts on the first, on the original one, action and reactions. So any two bodies with mass, in these slides, the Earth and the Moon, exert a force upon each other. It works for the Earth and the Moon. It works for the Sun and the planets in the solar system. It also works for the planet and satellites around it. Exactly the same equation. That was the great achievement of Newton. Practically speaking, what that equation tells us, and if you want, you can take my module in the next fall semester to show you how you can derive these. But there are essentially two types of orbits that we can experience in real life. I guess you as astronomers are very familiar with the first one because of Kepler's first law, which tells you that the planet in the solar system always move in an elliptic orbit with the sun at one of the focus of the ellipses. I guess recently as astronomers, you've also experienced the second type of orbit, which is known as hyperbolic trajectories. If you remember, a few years ago, there has been notification of an object that came from outside the solar system, Oumuamua. That object came very close to the sun and then escaped the solar system right away, going into the unknown. So I'm not cheating when saying that any spacecraft, as much as astronomical objects, can experience either elliptic or hyperbolic orbits. Now, an ellipse is characterized by two key quantities. Its semi-major axis is literally the distance between the ellipse and the center of the ellipse, and the eccentricity, which tells you how oblate is your ellipse. And as you will expect from Kepler's first law, the gravitational attraction, in this case the Earth, is occupying one of the foci of the ellipse. Due to Kepler, we also know that there is a relationship between the time it takes for a spacecraft to complete one orbit around the Earth and the size of this ellipse, its semi-major axis. And the equation is written up there. I don't expect you to remember it, but it's important to remember that the larger the ellipse, the longer it will take you to complete one revolution. Same reason why the Earth completes one revolution around the sun in 1 year, and Neptune in many, many more years. On the right, you see the effect of an hyperbolic trajectory. And really, the only thing that I would like you guys to remember from these slides for the next of the presentation is that on an hyperbolic trajectory, we are approaching our center of attraction from a very far distance. And if the object wasn't here, we will move in a straight line, right? But because there is a planet and because there is the force of gravity, that force has actually bent our trajectories. And the effect of that is that we emerge away from the planet with exactly the same velocity that we had when we approached it, but in a different direction. And that will come into play in a few minutes. Now, once we release our satellites from launch vehicles, we happen to be in orbit around the Earth, right? So in order for us to go and explore the solar system, we need to be able to change our orbit. We need to go from an elliptic orbit around the Earth, at the very least, into an hyperbolic orbit that will allow us to escape from the vicinity of the Earth and venture into the solar system. How can we do that? Well, space propulsion 101. There are 3 different types of propulsion technologies that I'm aware of. The first one is essentially a mini launch vehicle. Chemical propulsion, the same principle that allowed Goddard and von Braun to build the Saturn V, can be replicated on a much more smaller scale. The idea is that you have a combustion chamber, you inject a fuel and an oxidizer, there is a combustion, and that generates some exhaust, which are then expanded through the nozzle of a mini thruster and generate a push into a controlled direction. On the right, you see a much more efficient way of generating thrust. It's called electrical propulsion. Fun fact is that the first model of electrical propulsion engine does indeed go back to Goddard in the 1920s. But it's been put in practice for space exploration, actually by the European Space Agency at the beginning of this century with a mission called SMART-1, which tested this technology for the first time in space. And the idea is absolutely clever. You have like a gas, and you ionize the gas. What does it mean you ionize the gas? You divide the electron from the nuclei. And the nuclei that stay behind are positively charged. What that means is that now, with an electric or a magnetic field, I can control the motion of these charged particles. And the idea of electric propulsion is that you want to accelerate your ion away from your thruster so that you get a recoil in the opposite direction. Now, we say that electrical propulsion is much more efficient than chemical propulsion because the speed in which you accelerate this ion is significantly higher than the exhaust velocity that you get from a combustion. So why don't all of the missions are now built with electrical propulsion? Well, the problem is that ions are really, really tiny. So the thrust that you get out of this thruster is order of magnitude smaller than the thrust that you get with chemical propulsion. So things like ion engines are really useful for like controlling satellites. Like think about the big, large satellites that you have in the geostationary ring that allow you to communicate via your phone. They're nowadays all controlled by electrical propulsion. But if you need like a quick way to escape the Earth or quick way to control your satellites, chemical propulsions are still the norm. At the bottom, I wanted to put something which is something that we are actually studying in the Surrey Space Center, which is called solar sailing. And a colleague of mine is an expert of deploying this fancy structure from satellites. It looks like a sci-fi, but I can tell you we actually tested it in real life. The idea is that the photons coming from the sun impinging on a sail like that transfer some momentum. And by doing that, we have essentially access to an unlimited source of propellant because the sun is not gonna switch off in the near future. So photons will keep coming our way, impinging on that solar sail and push the spacecraft away into the solar system. Again, very efficient way, but really, really, really slow. And for some missions, as we will see, you can't afford to wait that much. Long story short, the idea is that with either of these propulsion technologies, you start from your orbit around the Earth and you can escape from the Earth. So what I show you here is an animation of a chemical propulsion engine, which has been fired anytime we come close to the closest point with respect to Earth and the satellites. And slowly but surely, but switching off my combustion chamber and releasing my exhaust, I can show you how the orbit of the satellites is changing. We're not really changing the distance between the satellites and the planet Earth at the point of closest distance, but as you can see, the size of the ellipse and this eccentricity is changing over time. Up to a point, which is gonna come up in a second, where we will eventually escape on that hyperbolic trajectory that I show you. And we are not coming back. So what happens once we leave the vicinity of the Earth? Oops. What happens is that as we move away from the Earth, remember the force of gravity depends as the distance square, right? So as we move away from the Earth, the gravitational pull that I feel from planet Earth is dying, is becoming less and less stronger. Another gravitational force takes over, and that's the gravitational force exerted by the sun. The sun is a much more massive object than planet Earth, so as soon as I escape the gravity of planet Earth, I'm gonna be dominated by the gravitational pull of the sun. But again, the same equations that Newton theorized applies. So as soon as I escape on my Earth hyperbolic trajectory, I land in a new elliptic orbit around the sun. Again, elliptic and hyperbolic orbits. And now we can choose where we want to go, because we are now free from the gravitational pull of the Earth. We are free to explore planets into the solar system. The ideal scenario is that as you escape from your Earth hyperbola, you enter into the trajectory that I show you here, which connects directly to the next planet into the solar system. In this case, I'm showing an unrealistic transfer from Earth to Neptune. But the idea is that I can draw an ellipse that connects the orbit of the Earth to the orbit of Neptune. And because I know what is the semi-major axis of this ellipse, I can calculate, first of all, what is the time it will take me to go from Earth to Neptune, and also what is the speed that my satellites need to have to leave planet Earth and go to Neptune. When you tabulate these values, you end up with some very interesting numbers. So first of all, if you want to go to Jupiter, you can insert into a transfer of this kind, and it will take you 3 years to get there. But you need to leave the Earth with 9.30 kilometers per second. Remember, I just told you, you need 7.2 kilometers per second just to get in orbit around the Earth. Now you need another extra kick of 9.3 to escape the Earth and go to Jupiter. Saturn, the next gas giant in the solar system. You can design a transfer like that, and you reach it in about 6 years. Still not too bad. I guess to see it, right? But as you can imagine, because we are going farther into the solar system, the speed that I need to leave the Earth with is slightly higher. And the farther I go into the solar system, the worse the situation becomes. Getting from the Earth directly to Neptune will take you 30 years. Hence, the reason why we still haven't had a mission that is dedicated to Neptune. It's very, very difficult to convince politicians and those who are paying for the mission that they need to wait 30 years before they get to see the results. Let me toss in now a curveball, because we had missions that have gone to Neptune and Uranus. The Voyager. And when you look at the time of flight it took for the Voyager to go to Saturn and the time of flight it took the Voyager 2 to go to Neptune, they don't quite match what I just wrote you into the table. So either I'm cheating and I don't know my math, or something else is happening here. And that brings me to the third part of my talk, which is interplanetary trajectory design. And I want to give credit to Dr. Michael Minovich, who unfortunately died in 2022. He was a JPL intern in 1961 when he came up with the idea, imported from astronomy, that instead of launching directly your satellites to Neptune, it's far more efficient to launch it first to Jupiter and then actually use Jupiter as a slingshot to get accelerated toward the next planet into the solar system. The idea was imported from astronomy because by the time Minovich ended up working at JPL as an intern, it was known that some of the comets in the solar system that flew by Jupiter experienced similar changes into their orbital elements, or the size and the eccentricity of their ellipses. So he had the audacity to propose that to his boss, who actually said, no, this is impossible. You're violating energy. And it took him 4 years to convince him that he was actually wrong. But the rest is history, because Voyager 1 did indeed launch on September 77, went to Jupiter, and you can see here how the gravitational interaction between Voyager 1 and Jupiter drastically affected its orbit, up to a point where for Voyager 1 was able to reach Saturn and then eventually move on deeper and deeper into the solar system. Nowadays, Voyager 1 is 166 astronomical units away from us, 160 times the distance between the Sun and the Earth. So let me try to illustrate this better with an example, because the idea actually is rather simple. If we accept that gravity is the dominating force, we can break our transfer, interplanetary transfer, into different legs. As I show you, once we escape from the vicinity of the Earth and we are subject to the gravitational attraction of the Sun, we are in what we call an heliocentric orbit, which is still an ellipse. Now, if the ellipse of your satellites happen to cross path with a planet into the solar system, all of a sudden, the gravitational pull exerted by the planet on the spacecraft will be much stronger than the gravitational pull exerted by the Sun, because the distance between the spacecraft and the planet is much smaller. But from a perspective of the planet, the satellite is coming from a very infinite distance, interact with me gravitationally, and then going away again to plus infinite. So from the perspective of the planet, the trajectory is actually hyperbolic. And once I emerge away from my gravitational encounter, I'm in a new elliptic trajectory with respect to the sun. So how does it work in practice? Let's consider the orbit of Voyager 1. It's elliptic, in orbit around the sun, is dominated by the gravity of our star. And at that point of this orbit, Jupiter is there as well. Jupiter is the largest planet into the solar system. So its gravitational attraction is actually huge. And we can see the effect of its gravitational attraction in the motion of the satellites around the Earth-Moon system. Now, from the perspective of Jupiter, Voyager is actually approaching from the x-axis of these lights. And we decide to fly behind the planet such that my hyperbolic trajectory will be tilted towards the left. So after my gravitational encounter with Jupiter, the new velocity of Voyager 1 looks like this. And I'm in a completely different trajectory than when I was before. Notice that I haven't mentioned spacecraft propulsion yet. This is purely the interaction between the spacecraft and the planet. And that's the beauty of gravity flyby. Because I'll show you into this example, that's exactly the trajectory that was flown by Voyager 1. Spacecraft was launched towards Jupiter, got accelerated towards Saturn, and there collected the first imagery of Titan, which is the largest of the moons of Saturn, proving that actually alien body can have an atmosphere, which later motivated the Cassini mission. And as an Italian, I'm very proud of that because there used to be a small lander called Huygens, which actually touched down Titan, proving that it's full of methane lakes and things like that. Now, what I love about these slides is that on the right, you see the difference the gravity flyby of Jupiter makes on the whole mission design of Voyager. If you were to implement the transfer that I show you there in magenta with the chemical propulsion engines that we talk about, it will take you 1,450,000 kilograms of fuel. Good luck in trying to bring that into space. Not happening. With the gravitational assist of Jupiter, 5 kilograms of propellant were enough to fly this trajectory. How about that as an enabling technology for space exploration? Now, I made it a bit simple because in reality, you need to find a trajectory that is crossing the orbit of Jupiter in such a way that once you fly by Jupiter and you are on a new heliocentric trajectory, you're also crossing the orbit of Saturn. So as you can imagine, timing is of essence. You need to carefully choose the departure date of your mission. You need to carefully choose the arrival date at Jupiter, and you need to carefully choose how you want to fly by Jupiter before you can go to Saturn. So unsurprisingly, 50 years later, myself and some of the PhD students at the Surrey Space Center are still actively working on interplanetary mission design. It's still an active area of research, which also inspired this very iconic scene from The Martians. We don't spend time in freezing into a supercomputer room. I can tell you I would rather enjoy a cuppa and wait for the results offline. But the reality is that we do use supercomputers such as the Eureka cluster at the Surrey Space Center to design trajectories like the Voyager 1. And I want to conclude this part of the presentation with two missions that are currently en route, which will hopefully inspire you for the next few weeks. JUICE is Jupiter Icy Moon Explorer, is a European Space Agency mission, which is going to Jupiter in 2031. It will be exploring the Galilean moon of Callisto, Ganymede, and Europa. Why? Because we think that actually all of these moons might harbor subsurface liquid oceans, which could have potentially the right conditions for life outside of planet Earth. In the center of these slides, you see the very complicated trajectory of JUICE, which involves a sequence of planetary flybys. We left Earth on August 2020, and what is it? Yes, Earth 2020. Then we came back to Earth in 2020, what is it? 2026 over there. No, sorry, 2024. We came back last year because last summer, if you remember, we made actually the news because JUICE is the first interplanetary mission that actually flew by the Earth and the Moon simultaneously, which was very, very cool to see. Now, the spacecraft is en route to Venus, and then from Venus, it will get the final kick to go back to Jupiter and ultimately insert into its orbit a few years from now. The other mission I want to talk about, it's Bepi Colombo, because it kind of brings what I've been talking so far together. Getting in orbit around Mercury is extremely difficult. Not only you have to deal with the crazy environment close to the sun. In fact, Baby Colombo is carrying a huge thermal shield to protect from the incoming sunlight. But you also need to think about slowing down from the orbit of the Earth, where Baby Colombo left, to the orbit of Mercury, which is the planet which is the closest to the sun. The only way we could do it is via that sequence of planetary flyby that you see. And on the top of that, we added electrical propulsion engines that slowly alter the trajectory of Baby Colombo in between the flybys. Sometimes things don't work as planned. And in fact, the last year when the team at ESOC, the European Space Operations Center down in Darmstadt, Germany, activated the thrust of Baby Colombo, they noticed that not enough power was transferred to the thrusters. So what happened is that this animation shows you arrival on December 2025. Sadly, that's not going to be the case, but the team at ESOC was able to understand the source of the error and redesign the trajectory for a new arrival in November 2026. So that shows you not only how complicated space exploration is, but also how crucial it's the work of space operators around the world to constantly assess whether we are on the trajectory that we design. Which brings me to the final topic that I want to cover before we go into some fun upcoming missions, which is deep space navigation. How do we assess the state of our satellite missions once they left the vicinity of the Earth? Well, I can tell you there will not be an interplanetary mission without a huge ground infrastructure to support them. And when I say huge, I really mean huge. Like, the Deep Space Network is perhaps the most famous example of communication facilities which are conveniently distributed around the world. I'll come back to this in a second, to constantly exchange radio signal with our satellites. Now, the DSN ground stations are 120 degrees apart on the globe. Why? Because the Earth spins, right? We rotate upon our axis once every 24 hours. So if my spacecraft is in this direction, sooner or later, it will fall away from the view of Canberra. But luckily, because my stations are 120 degrees apart, it will come in view into Madrid, and so forth into Goldstone, which is located in California, to ensure that I can constantly communicate with my satellites. Now, each of the Deep Space Network ground station facility has at least 3 times 34-meter antennas, and at the very least, 1 70-meter antenna. Think about 70 meters of satellite dish. That's what I mean by huge. And there are websites like this, which hopefully will work. Yep. Where you can see the Deep Space Network in action now. Here you see the ground station in Madrid. Here you see the ground station in Goldstone. And here you see the ground station in Canberra. This one, for example, is currently collecting and exchanging data with the mission Psyche, which was launched a couple of years ago towards what we think is a nickel core-rich asteroids into the asteroid belt. So very exciting mission that I can't wait to see the results of. Now, ESA, of course, as their equivalent of the Deep Space Network, we call them ESTRAC. There are 70-meter antennas in Malarc in Argentina, Cebreros in Spain, and New Norcia down in Perth. And there are other ground stations around the world which are a bit smaller, but they're still used to support deep space exploration, including Gunili Earth Station, which is just down by the Lizard. If you haven't been there, I highly recommend it, because it's not only a beautiful location for surfing, but it also has a lot of history, how the UK has actually supported the exploration of space, and still nowadays supporting the exploration of space. And they recently renovated Gunili 6, which is, I think, the big antenna that you see down there in the background, to align it with the ESTRAC standards. So the hope of Gunili Earth Station colleagues is to be able to enter into the ESTRAC network and to support deep space exploration in the upcoming years. So how does it work? Well, it actually goes back to a clever idea of Albert Einstein, which proved that in vacuum, electromagnetic waves travel at a finite speed, the speed of light. So if I generate a signal in my ground station facility and I ship it up to my satellites, then the satellites will beam it back down. The distance traveled is proportional to the speed of light times the time elapsed between when I generated the signal and I received it back divided by 2, because the signal traveled twice over that distance. So by using very, 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 very accurate atomic clocks into these big ground station building facilities, we can actually calculate the distance of an interplanetary satellite to the meter level. Meter level. And that's not even the craziest figure, because on the top of using this technique to measure the distance between the ground station and the satellite, we also use the Doppler effect. How many of you have heard about the Doppler? Of course, you're astronomers. So you know that far distant galaxies are actually turning red because they're moving away from us. The overall idea of the Doppler effect is that if you're moving closer to a source, the frequency of your signal is actually higher than the transmitted frequency. So if I know at what frequency my spacecraft will be beaming down the signal to the ground station, I can compare the expected frequency with the frequency I'm recording into my ground station, and that is proportional to how much the distance between the ground station and the spacecraft is changing over time. We call it the range rate. And the crazy thing is that we can measure the range rate, so the rate of change of the distance, with a 0.1 millimeter per second accuracy, no matter the distance of the solar system. That's how good it is. Unfortunately, sometimes it's not enough, because if I measure the distance into the radial direction, the Doppler also gives me just the rate of change into the radial direction. I don't have any information of where my satellites are in the plane of sky. The way we do it is to merge the signal of 2 ground stations, which are located apart, hopefully by twice the radius of the Earth, so about 13,000 kilometers. And then you can imagine that if the spacecraft is moving towards the right, then this ground station will receive the signal slightly earlier than the other ground station on the opposite side of the planet. Now, this works very well in principle, but as you can imagine, the Earth is surrounded by an atmosphere, and therefore, the condition that the electromagnetic wave is traveling into vacuum no longer applies. Our electromagnetic waves interact with the Earth atmosphere, and I guess as astronomers, you always deal with seeing and all the kind of degradation effects caused by the atmosphere of the Earth. So the way these techniques works, which by the way is called delta DOR, delta differential one-way ranging, is that if in the field of view of the satellite, there is also a quasar, which are known to be extremely accurate radio sources that have been studied by astronomers like you, and we have catalogs of them. So in the universe, there are many, many quasars that we can use as sources. And the idea is that if I compare the signal of my satellites with the signal of the quasar, and I differentiate them, I can remove all of the delays caused by the troposphere and the ionosphere of the Earth, which give me an extremely accurate measurement of where my spacecraft is in the plane of sky. That's it. I now finally triangulated the location of my satellites. And even if that is not enough, sometimes we rely on other techniques. As you can imagine, borrowing a 70-meter antenna with all of the spacecraft missions that are out there is a costly business. So one of the things that we are looking at the Surrey Space Center is how can we mitigate some of these navigation tasks to the satellites? And one easy way to do it is by using onboard cameras, because they're cheap, they're low power, and they're relatively simple to use, right? You just command shutter speed, and you process the picture. Now, this works very well if you already have a map of the body that you're exploring. Take, for example, the moon, which is shown in this picture. We have sent many, many missions to the moon. So we have a fairly accurate topography of the moon. Therefore, I can take a picture like this and compare with the topography map that I have on the moon to recognize craters. And if I have craters, I can use those as beacons to triangulate where my satellite is. Some of you may have heard a few weeks ago that the first commercial company has landed on the moon. It's called Blue Ghost 1. The company is Firefly. And this technique was actually crucial to enable that soft landing on the surface of the moon. So I like to think that moving forward, we're going to use more and more of these techniques, not only to explore the moon, but also other bodies into the solar system, including asteroids. And that brings me to the final part of my talk, in which I want to talk to you about missions that I've been working on as a senior lecturer in the Surrey Space Center. So the first one is the Martian Moon Exploration Project, which is led by the Japanese Aerospace Exploration Agency, where I had the luck to spend my 2 years of my postdoctoral studies. And the idea of MMX is that we will be launching in September 2026 and enter into an interplanetary transfer to Mars, one of those ellipses that I showed you at the beginning of the presentation. And if all goes according to plan, we will arrive at Mars in August 2027. The goal of MMX is to study the largest of the 2 moons of Mars, called Phobos, which you see here into this picture. And I also brought you a 3D printed model, which I'm happy to pass around, because it gives you the idea of how irregular this object is. It looks like a giant potato, and it's only 13 by 11 kilometers. So it's really, really tiny. So as you can imagine, entering into orbit around this object is extremely challenging. And on the top of that, Phobos happens to be only 10,000 kilometers away from the center of Mars, which means that if you go close to Phobos, not only you have to deal with the complicated gravitational field generated by that irregular object, you also have to cope with the gravity of Mars. My job at the Japanese Space Agency was to design the trajectories that you see at Deep's bottom, which was for the proximity phase of MMX. Once we get in the vicinity of Phobos, we are going to carry 3 years of extensive observations of the Martian moon, slowly but surely decreasing the distance from the planetary moon. We're going to move from 200 kilometers down to 30 kilometers. And let me put things into scale. The average distance between the Earth and Mars is 225 million kilometers. Okay? What I'm saying is that MMX will fly into trajectories which are 200 kilometers away from that potato-shaped like object. If I've done my math correctly, it's as if I was trying to fly a human hair through the eye of a needle, which is 10 meters away from me. And the fun thing is that we can do it using the navigation techniques that I just showed you. So why bother? Why Phobos? Well, there is actually now standing questions about the origin of the Martian moons. Because as you will see, as you will touch this object, is that it very much look like an asteroid. And in fact, Rachel, when first saw the model, told me, oh, it looked like an asteroid. Well, it could be. Because one of the accredited theories that actually Phobos and Deimos, the other moon of Mars, which is even smaller than Phobos, happen to be in the wrong place at the wrong time. Like passing by the gravity of Mars and getting captured by the gravitational pull of the red planet into orbit. The problem with that theory is that if you look at the orbital elements, the ellipses described by Phobos and Deimos about Mars, is that they're extremely circular and extremely equatorial. So what are the chances that 2 small bodies passing by Mars actually happen to be in the equatorial plane of Mars in the very small circular orbit? Tidal dissipation might explain some of it, but not all of it. So over the years, another theory came by, which is maybe Phobos and Deimos formed as much as the moon formed. So there was a protoplanetary impact between what then became Mars and a relatively large object that left behind a lot of debris that ultimately reaccreted into what are now known as Phobos and Deimos. Okay, that might explain it. The problem is, for the missions that we sent to Mars that took picture of Phobos, we can distinguish spectral signatures which are significantly different from the one of Mars. So when you take an image, you can also look at the kind of light that is reflected back to you, right? I guess you do a lot of spectrum of the sun, for example, to look at what is made of. And what happens with Phobos is that we don't quite make sense of the spectra as opposed to the spectra that we have of Mars. So we can't quite explain this dichotomy, hence why we are sending MMX to land on the surface of Phobos, capture some rocks, put them into a capsule, and bring them back to Earth by 2031. It's also being theorized that if we're ever going to send human beings to Mars, Phobos could actually be looking as a staging post. Reason being that it's much simpler, despite the challenges that I just talked about, to land on Phobos and return than to actually land on Mars and return back to Earth. As crazy as it sounds, that's what it is. Now, the important things about understanding the origin of Phobos and Deimos is that that has ramification on theories about how water has been delivered to Earth. There are theories that claims that comets and asteroids were actually responsible to deliver the H2O molecules that nowadays form our oceans. So I'm really looking forward to these missions. And just to wrap it up, when it comes to MMX, I want to show you these commercial videos that was made by JAXA, which basically summarize how amazing and fascinating is this mission? Launch vehicles, we've been releasing to an orbit around the Earth on an hyperbolic trajectory. So sooner or later, we are going to escape from it. Slowing them, okay? Crucial for the survival of the satellites is the deployment of solar panels that can then use the photons coming from the sun to generate power and support all the different subsystems of the satellites. We then deploy some landing gears. And after those 9 months of interplanetary cruise, we're going to make it to Mars. Here we use spacecraft propulsion. Remember, I talked about chemical propulsion engine. Look at how the satellites reorient themselves and then boom, fire its engine to slow down. Why? Because if it wasn't to slow down, it will move away on an hyperbolic trajectory further into the solar system. By slowing down, we are hoping to enter into orbit around Mars and ultimately in orbit around Phobos, where we're going to study the moon before landing on its surface. So here you see Phobos and MMX, hopefully in orbit around it, and ultimately landing on the surface of the Martian moons to retrieve the precious cargo that we want to bring back to Earth. We're going to spend actually a few hours on the surface of Phobos. This is different from a previous mission by the Japanese. You might have heard about the Hayabusa program, which recently brought back samples from Bennu, one of the asteroids. Those are classified as touch-and-go maneuvers. We really just touch and go away because we don't want to risk it. Well, in this case, we're actually going to risk it and land the satellites on the surface. But fingers crossed, if all goes according to plan, we are going to bring back the samples to planet Earth and deliver the capsule to the Woomera Desert in Australia for lab analysis on Earth. Okay, then the last mission I want to talk about, I'm going to test you because I found out that Professor Lucy Green gave a similar talk on this concept in January. So hopefully you're familiar with the Moon-enabled sun occultation mission. This is actually a concept that originated from my work here at the Surrey Space Center. Why should we care about meson? Well, as you can imagine, the sun is a very active star, and it generates catastrophic space weather events such as coronal mass ejection and solar flare, which, if they happen to be sent towards Earth, can actually pose significant threat for our planet. There was a very interesting article I read a few months ago. As you probably know, we are at the peak of the solar cycle. So the sun is really erupting and burping a lot of material at this moment. And last year, coronal mass ejection came together and ultimately affected agriculture in the United States for $650 million, just by causing disruptions into power grids and technologies that is underpinning agriculture in 2025. So as hopefully Professor Lucy Green and myself can convince you, we need better models of the physical phenomena that originate in the corona of the sun, in the atmosphere of the sun, to prevent these catastrophic space weather events. And our idea is to essentially enable very high resolution measurements of the innermost layer of the sun corona, very, very close to the sun chromosphere. Now, my understanding is that lots of you were at Newell's Corner last Sunday for a partial sun eclipse, right? Well, everybody will have wanted a total eclipse because they're much funnier and definitely much more breathtaking than partial eclipses. The problem is they're extremely rare events, right? They only happen once every 18 months on average. When they happen, they only last for about 3-4 minutes if you're lucky. And if you're really, really unlucky, you travel to far distances on planet Earth and then it's overcast or it's raining. So goodbye your observations. That can happen. And that's the reason why in the history of space exploration, a lot of effort have been put into putting coronagraph into space. A coronagraph is essentially a telescope with an occulting disk at the beginning, which is preventing the sunlight to come directly into your detector. And by doing that, you're hoping to reveal the light that comes from the sun corona. Problem is that due to the way you need to construct this coronagraph, you're going to introduce stray light and vignetting effect that essentially blur the image very close to the sun surface. So our current state-of-the-art space-based coronagraph can't quite access the innermost layer of the sun atmosphere where coronal mass ejection and solar flare originate from. The way we can shrink this obscured region is by increasing the baseline between the occulting disk and my detector. And last November, the European Space Agency launched out of India 2 satellites, probe-free. One will act as an occulter, and the other one will act as a detector. Very fascinating and inspirational mission. I can't wait to see the result. But in order to collect the images of the sun corona with that concept, you need to constantly trust your satellites. And that is introducing a heck of a problem because you're going to have a lot of vibrations into your measurements and everything's going to be very, very hectic. Which is why, despite increasing the baseline between the satellites, we're only going to be able to picture down to 10% of the sun radius. Still not quite enough for improving our understanding of corona mass ejection and solar flare. So what we want to do with MESOM is to fly near the apex of the moon umbra cone to recreate total solar eclipse conditions in space. And by doing that, we want to collect pictures like that one that was collected in 2024 in, I think, Illinois, during the great total eclipse in North America. Now, Professor Lucy Green, I'm sure, talked all about the science behind MESOM, but what I'm here today, and hopefully now you can see with me, how we can use lunar flybys and chemical propulsion engines to enable the trajectory of MESOM. So what you see here is a summary of what I talk about today, because hidden in this cluster of magenta points are flybys with the moon, which constantly change the orbit element of my spacecraft. And the stars are where I put chemical maneuvers using these miniaturized rocket launchers to, again, alter my orbit elements and enable occultation of the sun. So in summary, we're hoping that over 2 years, we will be able to obtain the equivalent amount of data of 50 eclipses on Earth, 400 minutes of total eclipse observations, which will provide a unique data set to hopefully better understand the catastrophic space weather events that originate in the innermost layer of the sun corona. And what's making scientists really, really exciting is that using this trajectory, we can enable 50 minutes of prolonged total eclipse observation. So imagine having 50 minutes of total eclipses with all of the dynamical effects being captured with a high-resolution imaging system. So yeah, please support MESOM. We have a big proposal coming up in May, and hopefully you will hear more about us in the coming years. And with that, I would like to conclude my talk and open any questions that you might have. Thank you very much. Okay.
Okay, does anyone have any questions? A couple of people being very shy.
Question for you about the solar silence. How far from the sun can they become affected? Because obviously the further one gets away from the sun, the less photon energy is going to be transferred to the sun. So there must be a limiting distance.
There must be a limiting distance. I don't know it on the top of my head, but I can tell you based on the numbers I gave you about the damages that corona mass ejection caused on US agriculture, they're very much significant for Earth. So all of the space-based technology, any electronics that is out there is subject to the radiation that comes from the sun. That's why not only it's important to understand this model, but it's also part of the national risk register. Like space weather is one of the threats that the UK is actively investing against too, because of how much we rely on satellite technologies nowadays.
I mean, there's been talk about using solar cells to accelerate spacecraft way beyond the edges of the solar system.
But it's using.
But is that feasible? Because you're getting out to the outer planets and outer parts of the solar system. Surely the pressure that you're going to get is becoming very negligible.
Yeah, so in terms of the talks that you're talking about to go outside of the solar system, you're talking about active solar sailing. They're talking about very futuristic concept in which we are actively beaming lasers to the solar sail to accelerate it from Earth, to concentrate the photons. Right. In terms of the history of solar sail, actually the Japanese Space Exploration Agency had a mission called Icarus that made it as far as Jupiter just using solar sail technology. So in terms of going into the solar system using solar sail, that's actually already been demonstrated. And then going back to your original questions, solar sail relies on the photons that comes from the sun. Those comes always, right? Corona mass ejections are highly energetic particles. They're not quite photons. They're actually protons that are the byproduct of the nuclear reactions that happens into the sun. And that's why they're dangerous, because they're heavier particles which are charged that can actually affect human beings. So as soon as there is a corona mass ejection, the astronauts on the ISS need to shelter as fast as possible into the, central part of the ISS, which is shielded just to protect them from radiation.
Great. Any other questions?
Does that mean you'd have to put your sail away during the coronal mass ejection?
Well, one of the mitigation strategies is to switch off take it back, because I had an interesting discussion with one of my colleagues, and he said that actually to mitigate damages on power grid, you need to power up all of the electronics. That makes it just more robust against charged particles that interact with them. But as far as satellites goes, you actually want to put them into safe mode, mitigate as much as possible operations, just to ensure that they will survive the radiation dose that can actually cause damage into the electronics. One of the things my colleagues at the Surrey Space Center discovered when they start launching satellites and pioneer what we now call the small satellite revolution is that by flying over a certain region of Earth, they will see glitches into their computer software. And for quite a lot of time, they weren't able to figure out what's happening. It turns out that's what is now known as the South Atlantic anomaly. There is like a dip into the Van Allen belt. So there is like a cluster of charged particles that constantly rotate around the Earth. And anytime satellites were passing into this South Atlantic anomaly, it was causing like glitches into the data rates and causing the satellites to move into safe mode. Satellite moving into safe mode, oh my God, what's happening? We need to figure it out. It's time that you take away from the missions, and that's money. So understanding these phenomena is crucial for enabling space exploration, in my opinion.
Great. Any other questions? I saw Tony's hand first, so I'll go up there.
Does the solar wind have any part in solar sails?
There has been,
as opposed to the photons, the material coming out.
Thank you for that, because if I go back to my Space Propulsion 101 slides, I should probably add a fourth figure, which is electromagnetic sail. So there is another concept, which is not using the photon of the sun, is exactly using the charged particles from the solar wind, like protons that are in there. But for this structure to generate enough thrust, they need to be massive. Talking about hundreds, if not kilometer square structures that need to be deployed and charged in order to interact with the solar wind. So I've seen concept, I've seen paper at conferences that I go to, but to me, they're a bit more futuristic than solar sail technology, which, as I was just saying to your friend here, they've already been flown and demonstrated that they can work in practice.
What's the comparison of energy produced by both of them? Presumably the photons produce more energy than the
it's not so much about energy, it's about the momentum that you transfer, right? And actually the momentum depends on the speed of the particle, and the photons travel at the speed of light, so they carry much more momentum than the protons into the solar wind, which are much heavier particles and usually 4 or 5 orders of magnitude less speed than the photons. That's why you need the bigger structures to capture more of them.
Great. Any questions on this side?
I'm just wondering, where do you get your finance for these missions? And is it government, private? And then is there a net, who benefits from the research? Who gets the net benefit financially from this?
Well, if we can predict space weather events and mitigate the damages caused by catastrophic space weather event, everybody benefits from it. Like 650 million is pretty much 3 times the amount that the MESON project will hopefully cost. So that already tells you, and we're talking about one single corona mass ejection event. Imagine projecting that over the years. In terms to your questions, depends on the type of missions. Nowadays, all of the interplanetary missions have been the domain of large space players, mostly America, Russia. China is now becoming a key player in space exploration, and the European Space Agency. But I'm hoping that with the Starship revolution and this drop into the cost per kilogram to access space, even a small institution like the Surrey Space Center can take their part into the space exploration. In fact, I'm pleased to state that we are currently working on a small side missions, literally the side of 2 shoeboxes put together, which will hopefully study the composition of water ice deposits into permanently shadowed craters around the moon. And that's done by students, by myself, by colleagues. It's still funded through ESA, but it's benefiting everybody in terms of supporting efforts to conquer the moon and also training new generation of scientists and engineers.
And of course, it depends on how much talent Americans put on us to use their spacecraft.
Well, yeah, nowadays, that's why we're submitting MESON to the European Space Agency. But yeah, no tariff. I mean, space exploration is surprisingly still, despite being 50 years after the Cold War, is still an enabler for international diplomacy. Yeah, so it's one of the big things where humanity can benefit, I think, from space exploration like this, because we won't be able to do all of these projects if we don't work together. And I don't see any harm in doing that.
I'll just come around the other side. Getting my steps in for the day.
How long is it until we'll be able to repeat the Voyager missions to the outer planets?
Ooh, that's a very good question. Because I actually address my 3 backup slides that I have here. There was another JPL intern in 1964, a guy called Gary Flandro, which is still alive. And using those expensive machines, the first IBM computers that were ever made, was able to find out that in the 80s, Jupiter, Saturn, Neptune, and Uranus were in a unique configuration such that it was possible to design what is now known as the Grand Tour. These favorable configurations only happens once every 176 years. So no, unfortunately, I won't be here to see it, but it's my heritage for my son to tell him to his son that he needs to work on that mission.
Any final questions? I think.
What's the latest research in aerobraking?
Ooh.
Yes.
Very good question indeed, because we have been talking about space propulsion, right? But one of the other enabler for space exploration is indeed aerobraking. And speaking about, I think the biggest challenge for probably the next generation of space engineers, I guess I might still be around, I hope to see it, but we need to send spacecraft to Uranus and Neptune. Neptune is still a bit far away, but Uranus, there are talks at JPL to send a spacecraft that not only goes to Uranus, but actually stays there. Because history has shown that by sending probes and to actually stay in orbit around them, like Galileo, Cassini, we learn so much more about the distant alien world. And the only way you can do it is Starship and aerobraking. So aerobraking is indeed a clever technique, is using the atmosphere of the planet to slow yourself down using aerodynamic forces. And it's for free, as much as gravity assists. So it's an active area of research. It's an enabler for Mars exploration, but hopefully also for the exploration of Uranus. So we are looking at extending aerobraking techniques, which have been successfully used for Mars exploration, to the gas giant Uranus as well.
I think we've got time for one final question. Perfect.
Thanks for the very nice talk, Nicola. So I think you briefly mentioned, I'm probably gonna like butcher the name, but Oumuamua, the object that like entered the solar system briefly.
Yeah.
And I think if I understood correctly, there was quite a lot of mystery about its trajectory because there wasn't that much time to take good observations of it, and it was quite far away. Are we going to be any better placed to observe the next object that comes in?
I've seen talks about missions. You probably heard about Comet Interceptor, right? And okay, so Comet Interceptor is a mission which is being approved, so it's in the making. We will see that happening. It actually came out of the UK as the lead. Muller Solar Space Laboratory down in Gomshall was the PI of that mission. And the idea of Comet Interceptor is to park a satellite in orbit around the Sun-Earth Lagrangian point, or I think the Sun-Earth Lagrangian point, to wait for when a fresh comet coming from the Oort cloud will be first detected, so that we can send the spacecraft to the comet and study it before it comes and interact with the sun. Because anytime a comet comes and interact with the sun, then it affects it, morphologically and also chemically, because you have so much energy exchange. The comet is full of ice, so as soon as the ice melts by being close to the sun, it rips apart the comet. There is very amazing footage by Rosetta once he was close to the sun, where basically all of his star tracker got completely shaded by the particles that were ejected by the comet, and they almost lost the mission for it. That tells you how much active a comet can be. And there are talks to do a similar concept for extra solar system objects like Oumuamua. So parking a satellite into an orbit such that as soon as we detect an object like Oumuamua, we can then relocate the satellites very fast to, see what they're made of. Are there new elements that have been built into different systems that we just don't know anything about? I think that's the quintessence of space exploration, right? But I think it's going to be hard to convince politicians that you need to park a spacecraft and wait, because waiting means that you still need to collect those expensive observations, and that obviously contributes to the cost, and you need to justify the cost of a mission. To go back to my friend that was asking about the cost, by the way, I have very interesting statistics. I assume everybody here has heard about Rosetta, right? The mission that went to a comet. How amazing was that? And I once found a statistic which says that the cost of Rosetta, considering the population in the EU, was 1 espresso, which in Italy is €1. All right? So wouldn't you pay €1 to see Rosetta and show it to your friends, to your daughters, your sons, and your nephews? 1 espresso, still cheap in Italy.
Great. Thank you so much. That was an absolutely fascinating talk. I think you managed the impossible task of getting quite a few astronomers excited about satellites, which isn't always easy to do. So thank you once again. That was brilliant. And if you give him a warm round of applause. So 2 things. Who has Phobos? There should be a moon floating around. Excellent. I'll come up and grab that in a second. We've got tea and coffee around the corner. It's £2. We've got a card machine you can tap in. If we could get back here, I think that's still an hour behind. 9 o'clock, 20-minute break.
I probably couldn't reach it.
So 20-minute break, and then we'll be back. We've got WhatsApp, we've got solar imaging talk, and then we've got lots of eclipse pictures from both the lunar and the solar eclipse, and some updates on what we've been doing in the last month, including at MSSL. So I'll look forward to seeing you then. Thank you.